All right, so this is for physics CP, but it really also applies across all of my physics courses and aerospace engineering courses. It's the same physics that we're going to be going over in this session. And what I want to go over is equations related to space travel and what happens in outer space. So, one of the equations to review, perhaps one more time, is called Newton's law of universal gravitation. Another equation is calculating centripetal acceleration. And there's two ways we can write that equation. The second way being 4 pi squared r divided by t squared. There's the equation for centripetal force, and that is mass times centripetal acceleration. I feel like I've done these well enough already, but I suppose it wouldn't hurt to just practice one more time doing equations like this one. So I'll start off with, and all of this is going to apply for circular motion only at this time. Circular orbits, circular motion, orbits, or moving something around on a string or an amusement park ride, orbits when the only centripetal force is caused by gravity, circular motion regardless of what's causing the inward seeking force, the center seeking force. So I guess as a warm up, I have a mass, and this mass is 2 kilograms, and it's at the end of a string, and the string has a radius of 5 meters, and it's traveling at a speed of, how about 4 meters per second. And my question is, so what is the centripetal force needed to keep this mass moving in that circle at that speed? Okay, so pause this video, calculate it. All right, so I agree with my students. When you plug this into the formula, you're plugging in 2 kilograms times 4 meters per second squared divided by 5 meters. So I've selected this particular form of centripetal acceleration. Then I multiply it by the mass. 6.40 newtons is the result that I'm getting. So the centripetal force in this example is 6.40 newtons. All right, let's do another calculation. Suppose I have a mass, and this mass has a value of 3,200 kilograms, and I have another mass, and the second mass has a value of 6,200 kilograms, and I don't know the distance between them. But I do know that the force of gravitational attraction between them is, minus sign just means that it's attractive, and this value is something like 1.30 times 10 to the negative, ninth power newtons. And the question is, what is the distance from the center of one object to the center of the other object? And that's what always goes into this formula. It's from center to center. So it doesn't matter what the physical dimensions are of either of these two objects. The question is, what is the distance from the center of one to the center of the other, using, of course, Newton's law of universal gravitation. So pause the video, calculate it yourself, and then play it and see if you got the right answer. Okay, well, unfortunately, none of 3 students got the same answer I did. So the way I solved this problem was first write down Newton's law of universal gravitation. The force of gravitational attraction between any two objects in the universe is an attractive force that is the product of the universal gravitational constant times the first mass times the second mass divided by the distance from center to center squared. And what's unknown in this situation is the distance from center to center. So I have to rearrange this equation algebraically to solve for this one unknown. And doing it slowly, I would first multiply both sides by r squared, and then I would divide both sides by the force. And finally, I would have to take the square root of both sides. That means r will be the square root of g, m1, m2, divided by the force of gravity acting between those two objects. So the numbers that I'm going to plug in are the square root of 6.672 times 10 to the negative 11th power newtons meters squared per kilogram squared times 3,200 kilograms times 6,200 kilograms divided by 1.30 times 10 to the negative 9th power newtons. So, plugging those numbers in, the square root of g times 3200 times 6200 divided by 1.3 times 10 to the negative 9th. Beep, beep, beep. And the result that I get is 1,009 meters. So to 3 sig figs, I would say 1.01 kilometers. Or 1,010 meters to 3 sig figs. So I'm taking that 0.9 and I'm choosing to round it up and write it without a decimal point. So there you go, 1,010 meters to 3 sig figs. All right, so now I'm going to move on and give you students a new equation to deal with. This one comes about by considering the Earth. So here's a circle, expertly drawn circle that represents the Earth. There you are, not to scale on planet Earth. If I were to ask you to calculate your weight, you would say, oh, that is great. That is just my mass times the acceleration due to gravity. But wait, I say, it is also the force of gravitational attraction between you and the Earth. That means it can be calculated using this formula, Newton's universal law of gravitation. Universal law of gravitation, abbreviated U-log on the internet. And in that equation, it says the force of gravitational attraction between you and Mother Earth is the product of the universal gravitational constant. Of course, it's an attractive force, so there's the minus sign, times the mass of the Earth times the mass of you divided by the distance from the center of you to the center of the Earth squared. If I ask you how far is it from you to the Earth, you might foolishly give me the wrong answer that says, oh, my feet are on the ground, and therefore the distance from me to the Earth is 0. Nothing could be further from the truth. The distance from you to the Earth is not 0, because we measure from the center of the Earth to the center of you. And the Earth has a huge radius. The radius of the Earth is 6,378.14 kilometers, is the value that I like to use, because that's what we use in our software program called STK as the average radius of the Earth. And by the way, the Earth is not a perfect sphere. So, average. You might be, well, maybe 2 meters tall. And so the center of you might be 1 meter above the surface of the average Earth. That makes it 0.001 kilometers above this average value of the Earth. As you can see, adding half your height to the radius of the Earth is insignificant. I mean, this is an average already to 6 sig figs. We'd have to go out even further to add your height to it. So we ignore you. You are small and insignificant, and there's the proof, relative to the scale of planet Earth for calculations close to the surface of the Earth. So within those constraints, the point becomes this: the radius of the Earth is the distance from the center of you to the center of the Earth. Even if you're Paul Bunyan, it's not going to make that much of a difference. Paul Bunyan being a mythological, very tall lumberjack, or Hagrid, or Robbie, giants. So the point is, if this is how we calculate the force of gravitational attraction between you and the Earth, G, mass of the Earth, mass of you divided by the radius of the Earth squared, and this is the same thing as calculating your weight by multiplying your mass by the acceleration due to gravity on the surface of the Earth, setting these two equal to each other, your mass cancels out. And what we're left with, without a doubt, is a formula to calculate the acceleration due to gravity on the surface of any planetary body where we happen to know both its mass as well as its radius simultaneously. So let's do a practice calculation for some hypothetical planet. Let's say I have an asteroid. Oh man, I know what program I want to run. I'm going to run a program that I wrote yesterday. And let's say that this asteroid has a radius of 700 and let's make it 7,500 meters. Okay, so this thing has a radius of 7,500 meters, 7.5 kilometers. So it's more than a mile in, is that right? 5,000 meters, no, 8,000 meters is 5,000 feet. So this is almost 1 mile in diameter. It's 7,500 meters in radius. Oh, so it's almost 1 mile in radius. So it's approaching 2 miles in diameter. And based on a program I wrote yesterday, that makes its mass somewhere in the neighborhood of 2.12 times 10 to the 15th power kilograms. I wanted to give realistic numbers in these made-up problems. So based on a density a little bit greater than ice, that would be an appropriate mass if this were a spherically sized asteroid with that radius. Calculate, please, what would be the acceleration due to gravity if you were a little spacesuited astronaut standing on the surface of this asteroid. Calculate, please. Well, 2 out of 3 students got the right numerical value, but no one seems to remember what the correct units are for acceleration. To solve this one, it's g times the mass of the central body divided by the radius squared. And so plugging in these numbers, the value that I got was matching 2 of the students, 0.002. Now that's only to 1 sig fig. The zeros are placeholders, so don't stop there. The second significant digit is a 5, and the next one is a 1. And the correct units for acceleration are meters per second squared. So there's a new idea I want to share with you students, and it's just a little math statement. And the statement goes like this. Suppose I have a planet of radius r, and I go above the planet 1 radius above the surface of this planet. So imagine that these are 2 concentric circles, and I'm now a distance of 2r above the surface of this planet. So originally I was standing on the surface, and the acceleration was gm over r squared, and now I'm in a spaceship, or I'm standing on some structure, whatever. I'm up here, a distance, an altitude, by the way, of 1 radius above the surface of the planet. And my question for you is, so what would be the acceleration due to gravity at this new location? Okay, so I called on one student, and he gave an excellent response that said, oh, well, look, I have doubled the value of r, but I have not changed the value of the mass. So what changes is not the value of the mass, only the value of r, and it has doubled. So if I put in 2r inside of parentheses and then square that, 2 squared is 4, but it's in the denominator. So the answer becomes 1/4 of whatever the original value was when I was on the surface. Sometime I want to give you a physics problem where you can't actually calculate the value on the surface. I'll just say I'm at a radius of 3r, or maybe I'll even tell you I'm at an altitude of 1 diameter above the surface of the planet, a radius of 2r above the surface. What's the acceleration due to gravity up here compared to the acceleration due to gravity on the surface? And I'm not going to tell you, oh, the value here is 5 or 10 or 0.00251. What I'm looking for is a response from you that says, oh, I am 3r as opposed to 1r. 3r squared is 9r squared. So the answer is I'm 1/9 the value that I would have on the surface. Okay, so it's just an algebra ratio where you don't have specific numbers being given to you anymore. It's a question of, all right, in this formula, what happens if I double the mass? Or what happens if I double r? How does that affect g? Okay, so that ends that. Now, I did bring up something already that I want to share with you. We're going to move on to circular orbits now. And in a circular orbit, let's consider the sun with the Earth, not the scale, orbiting the sun. We're going to pretend that it's a perfect circle. And as the Earth goes around the sun, there's two things going on. There is the force of centripetal force acting on the Earth. And what is that centripetal force? Why, that's the mass of the Earth times the centripetal acceleration of the Earth. If we knew the speed of the Earth and the distance from the sun to the Earth, we could calculate it. But wait, there's another way we can calculate it. And that is from that formula that said centripetal acceleration is not only speed squared over radius, but it's 4 pi squared times the radius divided by the period squared. So let's use this version of the centripetal acceleration and say, all right, we're going to calculate the centripetal force causing the Earth to not go flying off in space at a tangent, because that's what would happen if there weren't a center-seeking force acting on the Earth all the time. And instead of writing v squared over r, I'm going to write 4 pi squared times the radius of the Earth's orbit divided by the period squared. So two things to not get confused about. There is the radius of the Earth, which is 6,378.14 kilometers average. And then there's the radius of the Earth's orbit, which is what we need in this situation. They're both radius. That's true. They're both radii. Don't mix them up. Second, the period of time is not how much time it takes the Earth to rotate once, which is 1 day, almost. Actually, 23 hours, 56 minutes, 4.091 seconds when I was a kid. But instead, the amount of time it takes the Earth to go around the sun once. Okay, so be careful. 2 different radii, 2 different periods. Don't confuse which one you need for a given physics problem. The distance from the center to the Earth to the center of the sun on average is 1.496 times 10 to the 8th power kilometers. And the amount of time it takes the Earth to go around the sun once is 1 year. So if you're going to calculate the centripetal force acting on the Earth, you need to also know the mass of the Earth. And I would use a value of 5.974 times 10 to the 24th power kilograms. Okay? Armed with that information, keeping in mind that in this formula for centripetal force to work out correctly, the radius must be in units of meters, not kilometers, and the period must be in units of seconds, not years. Pause the video, do the conversions, and calculate, please, what is the centripetal force acting on the Earth in its presumed circular orbit around the sun. Some of you might have a question, how many seconds are in a year? There is an approximation that you could memorize that's pretty close, and that approximation is pi times 10 to the 7th seconds. But if you want to work it out a little more precisely, perhaps, you should use a value of 365, and let's just call it a quarter days in a year. It's actually closer to 365.23, leading to a non-leap year situation once every 400 years, but this is close enough for government work. Wow. Okay, so the fun thing about astronomical values is they are amazingly huge or amazingly vast in a lot of situations. In this situation, to calculate the centripetal force, the equation I used, of course, was the mass of the Earth times 4 pi squared times the distance from the center of the Earth to the center of the Sun divided by the period squared. Of course, the units have to be converted into meters and seconds for this to work out correctly. So the numbers I'm actually plugging in is 5.974 times 10 to the 24th power kilograms for the mass of the Earth times 4 times pi squared. For the radius of the Earth to go from kilometers to meters, I recall that 1 kilometer is 1,000 meters. So this 10 to the 8th kilometers becomes 1.496 times 10 to the 11th power meters. I have to go up in my exponent by 3 orders of magnitude. The time is 1 year, but I have to convert that to seconds. So open parentheses, 1 year times 365.25 days in a year times 24 hours in a day times, if you need to do it 60 times 60, okay. Otherwise, recognize that it's 3,600 seconds in an hour, close parentheses, squared. That's what you put into your calculator. So the result I got is 3.54 times 10 to the 22nd power newtons. All right. Now, I want to teach you some more this period. My next question becomes, what is the force of gravitational attraction between the Earth and the Sun? We have the mass of the Earth, we have the distance between the Earth and the Sun, and my question is, what is the force of gravitational attraction? Meaning I need to know the mass of the Sun, and I forget the symbol for that, times the mass of the Earth divided by the distance from the Earth to the Sun squared. Well, if I ask Lord Google, what is the mass of the Sun? It says something like 1.989 times 10 to the 30th power kilograms. Calculate, please, what is the magnitude of the force of gravitational attraction between the Earth and the Sun? No doubt you're using the same values from the previous problem because it's the same solar system. So the distance from the Earth to the Sun is 1.496 times 10 to the 8th power kilometers, units. And the mass of the Earth is still 5.974 times 10 to the 24th power kilograms. Okay, so my students and I disagree on the answer. Unfortunately, well. So it's an attractive force. I could always put a minus sign there to remind myself it's attractive. It's the universal gravitational constant times the mass of the Sun times the mass of the Earth divided by the distance from the center of the Sun to the center of the Earth squared. So the numbers I'm going to plug in are 6.672 times 10 to the negative 11th power newtons meters squared per kilogram squared. For the mass of the Sun, I'm going to use 1.989 times 10 to the 30th power kilograms. For the mass of the Earth, so I'm multiplying, I'm going to use 5.974 times 10 to the 24th power kilograms. And for the distance from the center of the Earth to the center of the Sun, again, I have to express it in units of meters, not kilometers. So that makes it 1.496 times 10 to the 11th power meters. And that quantity is going to be squared. So on my calculator, G times 1.989 times 10 to the 30th power times 5.974 times 10 to the 24th power divided by 1.496 times 10 to the 11th power squared. Enter. Beep, beep, beep. I get a magnitude of 3.54 times 10 to the 22nd power newtons. The force of gravitational attraction is 3.54 times 10 to the 22nd power newtons. So contemplate that for a moment, because we've seen that number before. That was the centripetal force calculation that we had just completed a few minutes ago to calculate what force is necessary to force the Earth to not fly off on a tangent to its orbit around the Sun. And the necessary force worked out to be 3.54 times 10 to the 22nd power newtons. Just now, we calculated the gravitational attraction between the Earth and the Sun, and that worked out to be the same number, 3.54 times 10 to the 22nd power newtons. This is not a coincidence. Contemplate the meaning of life here. The Earth is in a circular orbit around the Sun. The gravitational attraction between the Earth and the Sun is given by G m1 m2 over r squared. The centripetal force needed to force the Earth into a circle instead of going off at a tangent is mv squared over r, or m4 pi squared r over t squared. Either way you want to express the centripetal force. Speculate. What would happen if the force of gravity between the Earth and the Sun were greater than the centripetal force needed to keep the Earth from going off on a tangent? You should think about that and realize, well, that means the Earth would be pulled closer and closer and closer to the Sun. We would spiral in towards the Sun, burn up, and all die. On the other hand, what would happen if the force of gravitational attraction between the Earth and the Sun was too weak to provide the centripetal force needed to keep the Earth from flying off on a tangent? Why, then the Earth would start spiraling out farther and farther away from the Sun, and we would all freeze to death and die. It's been 5 billion years. And maybe the people in Texas would say, well, man, it is cold. It's been 5 billion years, and we haven't died yet from burning up or freezing to death. So from that, you should conclude that these two forces can be set equal to each other in magnitude. That Newton's law of universal gravitation, G m1 m2 divided by r squared, can be set equal to the centripetal force, which is m times v squared divided by r, in terms of magnitude. Do this. As you look at this new expression, you should notice that one of the masses is going to cancel out. The one that cancels out is in the situation of the Earth going around the sun, it's going to be the Earth. And so the only mass that ends up being relevant is the central body. So for the Earth going around the sun, that's a sun. For the moon going around the Earth, that's the Earth. For a spacecraft going around the moon, that's going to be the moon. The central body, the one that's in the middle of your circular orbit. That's the mass that goes here. And one of these radii will cancel. So if I multiply both sides by r, the r on the right expression is canceled, and one of the r's on the left expression is canceled. And cleaning up what I'm writing, it says, for an object in a circular orbit, the square of its speed is the product of the universal gravitational constant times the mass of the central body divided by the orbital radius. Okay, so I'm down to just a couple of minutes of class time. Let's do a closing calculation. So for example, let's do the sun as our central mass. It is 1.989 times 10 to the 30th power kilograms. Let's do the distance from the Earth to the sun. That is 1.496 times 10 to the 11th power meters. Calculate, please, what is the speed of the Earth in its orbit around the sun? Keeping in mind that was v squared. So the speed is going to be the square root of g times the mass of the sun divided by the Earth's orbit radius. Calculate, please, the speed of the Earth right now. Okay, we're at the end of the period, but my students worked out the correct solution. It's 29,800 meters per second. Every second of time, the Earth is going about 30 kilometers through space. And if I divide that by 1609 meters per mile, that works out to 18 and a half miles, not per hour, but per second. Every second of time, the entire planet moves close to 20 miles through space. Amazing and true. This concludes today's lecture.